Yeah, so Sarah, I forgot to start recording, so here you go. Here's everything we've done so far.
Hi, Sarah.
I'll explain it to you when you come back. Okay, so let's the rest of us keep going. Many chemical reactions require an initial input of energy. Most reactions don't happen all on their own. Some require a ton, like the demo that didn't work. We were lighting strips of magnesium. There was a lot of energy in a strip of magnesium, as Jedediah can attest to, because he was here and on Monday and did the lab where he was allowed to burn magnesium on his own. Lots of energy is released there. It's very bright, it's very hot. And still, for some reason, the aluminum and the iron oxide did not ignite for you guys. The reactants will not react by simply mixing them. In some reactions. But lots of the reactions that you guys have done already for me, especially in that iron chemist lab, required no additional energy. You took the one test tube, you took the other test tube, you mixed them together, and the reaction happened immediately. Two colorless created a white solid and a colorless liquid. The reaction happened on its own. So many chemical reactions require the initial input of energy, but not all. So it says many here, but I'm going to say not all. I'm going to add that in there. And then, for example, lighting a propane barbecue requires a spark or a lighter. The oxygen in the propane isn't going to spontaneously combust, which is good. This energy input needed for the chemical reaction between the oxygen in the air and the propane gas, that initial amount of energy is the activation energy. The lighter provides a few molecules of oxygen and propane with enough energy to overcome that propane barrier. And all you need is a single spark, because the formation of bonds releases more energy. So I'm going to draw this out here for you. Propane is this, C3H8. So we're going to draw out a propane molecule down here. H, 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 H. And here's O2. Propane is a big molecule. Oxygen's a little molecule. A spark is all that is needed to break all of these bonds. And then once you break the bonds, there's going to be an intermediate state here. You're going to have a bunch of C's floating around. You're going to have a bunch of H's floating around, 3, 4, 5, 6, 7, 8. And you're going to have some oxygens floating around here too. On their own, they are not pleased because they've got space to take in electrons. These are all nonmetals. And so they all want more electrons to themselves. And so from every combustion reaction, you're going to get what two products? CO2 and H2O. Every combustion reaction is going to do that. So every carbon is going to find two oxygens. And all of the hydrogens are going to form up with the oxygens to make water. And so you're going to get all of these H2Os forming. I need more of them. There's another one, that's 6. That's 8. Those are all my hydrogens taken up. These are all my carbons taken up, which means I need a whole bunch more oxygens here to have been broken. But if you look here, we broke, how many more do you have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 6, 8, 10. We broke 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 bonds. And that required a particular level of energy. But these bonds, when bonds form, they release energy. So we formed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We've created 20 more bonds. And the act of creating all of these other bonds releases more energy. So the energy that gets released here is enough to set a chain reaction up so that more propane and more oxygen have their bonds broken, so that they can form more of these. So then those new bonds forming will release more energy, which will continue the chain reaction of more propane and more oxygen getting broken, which allows these to form, which breaks more energy, which is why a barbecue only requires a single spark to start, and then once it's going, it will continue until you cut off the source of propane. Because this releases a ton of energy into the surrounding area, energy in the form of heat. This requires energy to go in. This is enough energy to go in here to continue that reaction. It's a simple example. When you're ready, flip the page. Sorry? What do you mean? You want me to write out the paragraph that I just said? Oh, to be able to explain it yourself? There was a lot there. Maybe not to that level. Okay, so everything I've just shown you is all about, there's a teeny tiny little bit of activation energy, and then once you break the activation energy, the reaction goes, releasing a ton more energy. That kind of reaction is what's called an exothermic reaction. An exothermic reaction is a reaction that releases more heat. And a reaction that releases more heat than is required for the reaction is going to feel hot to you. That was a fun sound. I don't know what that sound was. But there's another type of reaction. You guys have done some of these reactions. When you mix chemicals together, if you've held the test tube, it might have felt warm. Hands up if you've ever done a reaction where you mix the things together and all of a sudden now it feels quite cold. Why did you put your hand up for a second, Brooklyn, and take it back down? Oh, okay. Hands up if you've ever used a cold pack. Like you've had a sports-related injury, and what did you have to do, Hobkirk, to the cold pack to get it to work? You have to shake it. Or Evelyn, what did you have to do? No, I don't want the heat packs. I want the cold pack. No, that's the different kind. That's the one where you make it cold and then it gets warmer. You've actually had one where you have to shake the bag or crack something in the bag, and then on its own, it just spontaneously gets cold. You break a barrier inside there, and you allow things to mix. What you've done is you've created a reaction that is not exothermic, where it gives off heat. You've created a reaction that is endothermic. This should be E-N-D-O. I don't know why it got cut off there from the photocopier. Endothermic. An endothermic reaction absorbs heat. It draws in heat from its surroundings, and if something starts to pull heat out of you, it feels cold. That's what feeling cold means. Your guys' experience of feeling cold just means that your surroundings are pulling out energy from you and not giving you any. If something feels warm, that means the atmosphere is hotter than you are, and so it's forcing energy into you. That's why you feel hot. If you don't feel hot or cold, just comfortable, it means you and your surroundings are operating at the same temperature. Yes, Evelyn. Keeping the heat contained is going to start to jack up. It's going to start to feel hotter if you're not letting it go anywhere. Okay? So endothermic absorbs heat, feels cold. Exothermic releases more heat, feels hot. If you recall, Energy must be absorbed to break bonds, and energy is released when bonds form. By comparing the total energy used when bonds in the reactants are broken with the total energy released when the bonds in the products are made, you can determine whether there is an overall release of energy or an absorption of energy in a chemical reaction. This is, and we're not going to do any of these calculations. These calculations come later, Chem 11, Chem 12, University Chem. Just the concept that this exists and happens is what we talk about in Science 10. When overall, more energy is released into the surroundings than is absorbed, the reaction is called exothermic, and you feel it to be hot. When there is an overall greater amount of energy absorbed, taken into the reactants by the system than is released, the reaction is called an endothermic reaction, and it feels cold. So an example of this would be this reaction here. The reaction that happens when O2 and N2 react to form NO. This is a reaction that some of you may have seen last year in the ecology unit of Science 9. You guys, if you were taught the ecology section, if you had me, you didn't see it. You look at the cycles, the carbon cycle, the nitrogen cycle, the oxygen cycle. Hands up if you looked at the and the phosphorus cycle. Hands up if you talked about the cycles last year in Science 9. It's hard to get to. Did you have Easton? He usually does it about a week. Yeah, about a week right at the end. It's hard to get to because there's not a lot of time. In there, you'll talk about the nitrogen cycle, and part of the nitrogen cycle, to get everyone needs nitrogen in their system to a degree. To get the nitrogen into you, it has to come out of the atmosphere. The atmosphere is about 70% nitrogen. 73? It's a large percentage of nitrogen. Your body doesn't do anything with it. You breathe it in, you breathe it out. It does nothing. To get it out of the atmosphere, it needs to go through a process called nitrogen fixation, and here's why. Oxygen on its own, the Lewis diagram looks like this. The Lewis diagram for nitrogen looks like this. There's a triple bond there in the nitrogen diatomic molecule. Breaking all three of those bonds to get nitrogen on its own is a lot of work. This is called nitrogen fixation. Easton, I think, is the only Science 9 teacher that I know of that gets to this. I don't think Mr. O did last year. Nitrogen fixation requires lightning to happen. Lightning strikes break up. It's one of the things that breaks up the nitrogen. Like, it's a lot of energy. And when these things get made, the nitrogen and the oxygen bond together with these double bonds here. The amount of energy required for this to happen is large. There is a very large activation energy required to make this happen. So the curve actually looks like this. The oxygen and the nitrogen are stable on their own. They have a very low natural energy. A lightning strike is created and is necessary to break this activation energy. This here, this big hill, that's the activation. And then NO is not as stable as O2 and N2 were, so its inherent natural energy is going to be higher. The NO is up here. The energy that goes in is larger than the energy that comes out, and so this reaction here is going to be endothermic. It feels cold when this reaction happens. Never mind the lightning. Comments, questions, concerns on what you've just seen? Okay. So, I have some practice that I want you to do. I know there's only 10 minutes left, but the practice isn't a lot. Here's what you're going to do. There are 4 questions here. Based on the description, all you have to do is tell me whether or not the reaction is exothermic or endothermic. And then I want you to flip over, and I want you to look at these pages. There are 2 sets of graphs. There's this graph here. This graph represents the fact that the reactants have this much energy. There's a little hill to get over, and then there's a big hill on the other side. The second one looks like this, where you've got a large hill to climb and then a small hill to come down. I want you to do those 3 pages. We're going to leave the very, very last page, because this very, very last page is going to look an awful lot like the lab that you're going to do for me tomorrow. You guys are going to do a lab tomorrow where you do 2 reactions. You're going to mix a set of chemicals together, and you're going to graph the temperature change. And so you're going to get something that looks like this. The temperature started higher, and the temperature ends lower. Or the temperature might start lower and end higher. You're going to take a look at what happens. You're going to identify the reaction as either exothermic or endothermic, and you're answer some questions about it. So what I'd like you to do now, just the first 3 pages, tell me if it's endo or exo, and then page 100 and 101, that's your homework. I'm going to call a few of you up to talk to you about missing work in the next 10 minutes. And then when the bell goes, you can go. Have a good day.